Hello and a warm welcome here from the Joanneum Research Robotics Evaluation Lab. Within the next 3 minutes I will present you the current status of the ForSAMARA research project. ForSAMARA is funded under the H2020 project RobMoSys. The participants are from Joanneum Research Robotics, the TU Wien and PILZ. Our goal is to verify safety properties on collaborative robotic applications. To illustrate our approach, we set up a demonstrator using a Franca Emica Panda robot. We formally check the application for collisions between the robot's DCP and static environment objects. If such a collision event occurs, we simultaneously assume that there is the risk of clamping a human body part. This image here shows the full set of tools and models which are used for the implementation of our demonstrator. On the upper side you can see that we define the skills of the robot application and the workflow which defines the execution sequence for these skills. This is done by using the behavior tree model directly implemented in the Papyrus for Robotics toolchain. This behavior tree is then transferred to a verifiable model representation which can be used in our new XMV model checking tool. However, since the movements implemented by the robot are not linear, we use a trajectory engine tool to get them more realistic. On the second part you can see we model the environment by using an octomap representation. This octomap representation is a very effective modeling scheme for environments in general. However, this octomap is then transferred into a constant voxel-sized format which is also integrated in the verifiable model. On the lower part you can see we defined our properties which are based on the standards and laws given by all the national authorities. On the first side we define application-specific rules which are highly bounded into the specific robotic application. On the lower side you can see we define some general rules which can be reused for several robotic design projects. On a further step we define semi-formalized properties which already holds the operators from the model checking tool, but in the combination with natural language parts. After the mapping of the natural language parts into the specific variables implemented in the model, we can derive the set of LTL properties which are then finally checked on the verifiable model. And last but not least, we get our verification results. This sequence shows the execution output of the model checking tool. The log returns that a collision is detected by setting the highlighted bit to true. If we check the collision position in the 3D model, we see that it occurs at the approach of the robot to pick up the cubic workpiece. The corresponding collision voxel in red represents the table surface. Strictly speaking, the voxel is that large that the robot's target position is inside the table. This can be solved if we double the resolution of the environment voxel model. Then everything is fine and the modeled workflow is formally verified to be collision-free. Our currently implemented demonstrator is a simplified model, but clearly shows the essential concept and methodology of the proposed modeling process, as well as the steps towards formally verifying safety properties. Thank you for your attention.